Okay. All right. So today I'm talking about a paper. One second. I forgot the paper. Did you sign your name there on that paper? Oh yeah. You stayed here last night. How do you go home? You walk. That's not right. It's a little weird. Okay. So the main idea behind this paper is how to constrain a neural network layer to have the same or similar topological properties as whatever your input data is. Topology is essentially the subfield of mathematics that studies how certain properties are maintained under what's called a homeomorphism. A homeomorphism is simply any continuous function that is bijective and has a continuous inverse. So some examples are things like stretching, bending, and twisting. Maybe you've seen it before, but like a donut and a mug can be considered the same thing. They are homeomorphic to each other. The example that I think most applies to us is that if you have two matrices, Q and P, Q and P does not equal PQ, right? But you can deform QP in this equation. Like this is kind of a canonical thing, I think. I think we should all be aware of it. That's a homeomorphism. So PQ does not equal QP, but they are homeomorphic to each other. Okay, so one big part of this paper and topology in general is given some higher dimensional space, can you break it down into subcases? One form of that is called the simplicial complex. So a simplicial complex is you have some object and you break it down to points, lines, and triangles of n-dimensional space. So maybe you have n-dimensional triangles, whatever. And they're ordered by the nth dimension to the 0th dimension. So we'll take this diagram. The 0 dimension is all of the vertices. So if we see in this torus, I don't know if you guys can see it very well, but in this torus, there are 9 points covering the object. Those are our 0th dimensional simplices. The one-dimensional simplices are the lines, the edges. So you can see them colored in yellow, red, brown, orange, blue, green, and black. There's a total of 27 line segments. Then the 2-dimensional simplices are all of the triangles. You can see a total of 18 of them. So that's what your set becomes. 18 triangles, 27 lines, 9 points. And within these simplices, is that the next? Yeah. Within these simplices, there are boundary maps. So the boundary maps are, it's kind of somewhat obvious. They're whatever the boundaries of the object are. So a triangle has 3 boundaries, the 3 segments. A line segment has 2 boundaries, the 2 points that encapsulate it. Okay, so a homology is at each dimension of this complex that you can represent that complex as a vector space. So maybe it's points in three-dimensional space, maybe it's something more abstract, or it's an algebraic structure. It doesn't necessarily matter, but it's defined by this function, which is the kernel of the lower, delta K is this simplicial function from dimension K to dimension K minus 1. And so this function, this boundary map, essentially, so it's in essence this boundary map, or mapping rather. The kernel of this boundary mapping is all the points that map to 0. So when you're going from a triangle to a line segment, everything on the inside of that triangle is now mapping to 0 because it doesn't exist anymore. The only thing that exists is the boundary. In a line segment, the actual edge, the line itself, maps to 0, and only the two boundary points remain. So that kernel would be that edge, the thing that maps to 0. The image is the output, the two boundary points. And so this kernel over the image defines the thing that maps to 0 over the boundary condition. I think that's, it's a little complex. If there are questions, I can talk more about it. But I think the kind of takeaway here is that given some, anything, given any kind of object, maybe it's a picture, maybe it's an actual geometric shape, maybe it's in 3 dimensions, whatever your input is, MNIST, those digits are geometric shapes. CFAR, geometric shapes, although those are probably a little too complicated. You break them down into their points, segments, and triangles. And then you take the boundary conditions of all of those shapes and use those as a way to kind of structure how the points grow. And so how the points grow or change is called a filtration. It's defined loosely as the closeness, but really the basic example, I think, is the best way to do this. If you have, you can see from the image in the slide, I think, if you have a certain amount of points and you draw a disk around each point based on some radius, which in this image, the first one, it's radius 0. So they're just 4 points. They don't have a disk around them. The second diagram is the radius of the square root of 5, which now gives us, instead of 4 points, 2 objects. The 2 circles that have meshed on the top side, and then same on the bottom. When the radius is the square root of 10, we now have 1 object, which is in essence just this loop, just this one big kind of toroidal thing. As we increase, we are reducing the number of objects. This reduction is important because this is how we're going to define this homology, and rather this persistent homology. So how do the objects live? If a point, we'll go back to the example of the Euclidean radius. If a point is always existing, no matter what the radius is, maybe it's the only point in the space, then it is persistent across your entire spectrum. This diagram, hopefully, I think sums it up pretty well. So what we're measuring with this persistent homology is when the object is created and when it dies. So, I gotta wait for the gift. Okay, so at no radius, nothing exists. At the 0th radius, they're all points. And then if you see where they end, the blue dots along that line, that's where the points are dying. So we'll go back. You see here, all of those points are now merging into one, and we also see the creation of new objects. So within this whole circle, there are small holes that are being created. If you know, when it cycles through, you can kind of see them. Those holes are now new objects. And so that's why you see new objects being created along the x-axis, which is the birth. So at radius, let's say 0.03, new objects are being created. At radius, I guess 1, at radius 1, all of the objects die except for this last disk. I guess it's not 1, it's 0.6, let's say. At the radius 0.6, there's only one object now, just this whole disk across all the points. And that's when everything, that circle has died. And so all the points are dead at that point. Are there questions? Okay. This persistence diagram, the thing I just showed, can now be represented as what's called a barcode. This barcode is essentially the time or the difference between the positions of the change in radius. Represented now as this length. So this diagram's a little complicated, but if you think of each point as having some lifetime, when it's born and when it dies, that's now its bar, is the point at which it lives. So I'll go back to the last one. All points in here have a birth of 0. When we create those holes that you see, those holes have a birth of whatever, 0.3, 0.4, 0.5. And some of those points have a death at 0.3, 0.4, 0.5. And that would be reflective in this barcode. So hopefully that makes enough sense to get to this point. The paper turned all of that into a loss function. So in some layer, it doesn't matter, often it's the output, but it doesn't really matter. You can have this constraining loss function. So just like we have in VAEs, in essence, regularizes whatever you need it to regularize based on topological properties. So in this loss function, it's just the length, D minus B. So D is the death, the point at which it dies, and B is the point at which it is born. So it's that length of that barcode. Now P and Q their definition is out of the scope of this paper. It's based on previous research and it doesn't necessarily matter. PDK is just the filtration, it's just the distance. It doesn't matter for, like, it's kind of been discussed. I0 is what? The lifetime that you care the most about. So like, do I care about anything that lived over size 2? So if DI minus BI is 2, I only care about those things. And just because the IK is sorted, so the most persistent things are, okay, so the point. Okay. Are there any questions? It's a complicated topic. And
yeah, what is the whole purpose of, what the paper wants to achieve?
Okay, so there will be some examples, but I think the core idea is if you regularize something to keep its topological properties of the input, you're going to get output or maybe generated images that are more reflective of your input data. And put another way, because topology is most concerned, is in layman's terms concerned with holes in the object, you're essentially reducing the number of holes. And so this is an example where so that is our input, that is our data on the left. It's just a circle. So our data is generated from that circle with some noise. And in the middle, it's just OLS, linear regression, trying to reconstruct the sample data. Reconstruct each sample input, where the sample input is some noisy version of the thing on the left. And so as you can see, like it doesn't know what it's doing.
What is the right side?
The right side, that is with the topological loss. And so you can see that it's actually maintaining that topological shape really well. And in kind of more simple terms, it's essentially reducing the number of holes. So it's reducing the number of disconnected points. In the middle, with regular OLS, we see a lot of disconnected points. There's a lot of black space in the middle of this object. The black space, the holes, meaning a disconnect where in the original input, it was connected. And so it does really well for this. I mean, this is just one example. Yeah.
Can you go to the previous slide?
Yeah.
So I have this question on what do you mean by the third point, the sum of the for the sum over lifetimes, starting with either the longest living point. So by longest living point, if I refer to the GIF which you showed, so which is the longest living point in that case? Okay.
It's a little messy. Hold on, I gotta click on my laptop.
But guys, hang on a second. Simple version is, I think they're doing persistent homology, which is just to say that it survives more of the filtration. Like you're just doing more and more refined filtrations. I mean, I think that's okay. I won't pipe in too. I think that's kind of like the simple answer.
Yeah, that's it. The thing that persists longer. It's because it is just, the death minus the birth. So you're saying like I believe it's the index, although I'm not positive. I believe it's the index of the point that survives the longest because they're ordered. Robin, you can correct me if I'm wrong.
So for each iteration, what I understood, for one point, my radius for that will be increasing, and I'm basically decreasing the holes which is there in the whole set. I'm just trying to reconnect it with the GIF you showed in the previous slide. So in that case, when I'm going, when my line is going, above, like this one, when my red line is going, when it's increasing, you can see there are no points which are getting generated. So in this case, the longest living points will be the below ones, which is near zero, or
so the longest, it's hard to, okay, actually, if you look at the top right, there's a point that's kind of distant from all the others.
Right.
Yeah, that's probably the longest living, or maybe actually rather, the longest living would be the disk. Sorry, not disk, but the circle. When they've all formed this circle, there's a better name instead of circle, but whatever.
Okay.
Because that lasts for a whole 0.5.
Right.
And on the 2 slides later than this, after one. These are on image data.
Yes.
And so this topological loss, is it applied to the image itself or the higher order representations of the data?
It is applied to the output.
OLS.
So the OLS is, so we have, the left is our actual image. And then all of our samples are noisy representations. We basically have a noisy sampling of this circle. And then what we're trying to do with OLS is reconstruct that input sample, the noisy representation of the image. And so this loss is on that reconstruction. So the reconstruction would still be, WX plus B, the OLS, plus these two loss functions, where each of the loss functions represents the dimension. Dimension 0, dimension 1.
And one other little, like I'll pipe it, I'll try not to pipe in too much, but obviously the topology is only happening at that layer. There's nothing topological about the final loss function, since the circle, the reconstruction would be just the same topologically if it were smaller, if it were oblong, if it were elliptical, right? Like topologically, the topology is a layer-wise function of this filtration, of surviving a filtration of greater and greater radii, or possibly the other directions, probably greater radii, right, of consideration of proximity. And then at the end, you just do a normal thing.
Well, so in this case, there's only one layer.
Okay. So the only layer then is
because all it is OLS trying to reconstruct the noisy image. Mm-hmm. So then the loss is at the same point of the OLS loss. Is that
right? Yeah, no. I mean, I kind of know. I'm just saying, like, that isn't a topological loss function, even though there's a topological.
I see your point.
You know what I'm saying? Like, I mean, it could be a 4 mile long ellipse and still be topologically equivalent to what it just reconstructed. So,
yes.
Right? Yeah, that's all I'm saying.
Yeah.
So yeah. Okay.
Sorry. Yeah. Okay. Did that answer?
Kind of. Yeah.
Okay.
I'm still not sure about what would the output of that OLS look like.
Yeah. Maybe I have the same or similar question that subject has. So my question is, okay, I understand that you are trying to reconstruct this noisy sample, right? By applying topological penalty on top of OLS solution, right? Mm-hmm. So what is the purpose of doing that? Why are you doing that?
Why am I adding the topological?
Yeah, I'm saying what is at which position of the machine learning pipeline this phase will be used. That is what I'm asking.
So in general, it can be used at any layer. In this specific case, it's just linear regression, right? So it's just MLE, whatever, I don't know, of WX plus B. However you want to define that, I don't think it matters. That loss plus these two other loss functions, the two topological loss functions. So there's only one layer, right? It's just WX plus B, and then OLS, MLE.
But I think the regularization here, it actually means that you have to use it. I mean, you normally use this when you're going to define a loss anyway. So loss plus regularization is what you do, like L1 regularization or L2. So is it just like that? Are we just adding? Are we using some other kind of regularization? Is that what you're saying?
In this case, it is the topological regularization. Yes, on the output.
Yeah. Sorry.
So what is it trying to achieve? The regression or classification or clustering?
Reconstruction.
Yeah.
Just reconstruction.
Yeah. So the one in the middle, it's trying to reconstruct a sample.
Interesting that a linear regression is being used for a reconstruction purpose.
It's
just an example. It's most of this is the guy who wrote this is a topologist. He works in topological data analysis. and he wanted to turn this thing into the persistent homology into a loss function. And so these are just kind of examples.
So
it's a simple example,
may I think of these example similar to autoencoder?
Yeah.
But I'm saying similar to autoencoder, but functionality is different. The algorithm is different.
Yeah, that's why I said it's interesting, because autoencoder will be used for not reconstruction, basically making the exact image, kind of the exact image, but you can also add the noise and everything, but here you're just using a linear layer itself. You're not even, I mean, if I say linear regression, I'm just using like one layer and that's all. And that's being used for reconstructing an image. For autoencoder, you actually need a lot of layers in order to reconstruct or even come close to that image. So it's really interesting that they're using just by using that loss function plus that regularization technique. Is
it trying to achieve some improved embedding of the input?
Embedding, no. It's trying to improve the output. So we're trying to reconstruct the original image from the noisy samples. That's our original.
Yeah, the reason I am asking this.
Yeah.
You know that, as I know that autoencoder is used to get an embedding of the input, but through reconstruction.
Yes.
Right? Yes. So in the middle, you will get an embedding, but that improved embedding will be achieved through reconstructions of the input.
Yes.
Right. So is it similar to that kind of?
Conceptually, yes. And what we'll see next is more what you're talking about, and not in the context of an autoencoder, but a different generative model. Again, so, you know, the basic GAN or whatever is just this generator. It learns to generate this image based on a discriminator saying whether the image is real or fake, blah, blah, blah. So and this is on MNIST. So A is with just the regular GAN. So the discriminators has been trained, it knows what a fake image is and what a real image is, and those are the generated images. On the A is the generated images from the baseline GAN. B is with this topological loss where the generator weights are fixed. So this generator outputs some image and there's some loss on it, on that image. The topological loss is on that image. And then they use the SGD to update the discriminator weights to reduce that loss on the image. And so that's how we get this other set of examples. And this is just my conjecture. I don't think they quantify this, but you can see that there are fewer holes in B than there are in A. There are fewer disconnected points. Because in MNIST, there really, not many people have disconnected numbers. They don't often draw disconnected numbers. Some people do. I think that happens with 8. But I actually think this is a pretty good example of how this loss function could actually benefit us. C is the example where the generator weights are no longer fixed. So they train both the generator and discriminator weights based on this topological loss. And I think those look pretty good. I mean, you may disagree, I don't know. I think they look pretty good, personally.
Hey, Noah, a quick question.
Yes.
So are they, what they're doing, yeah, they're working like with the idea of just like porosity or whatever, you know, at certain scales, right? In the layer, that's basically what they're working with. And then, but the question is, I haven't read, of course, I have not read the whole paper, but are they assuming that continuity is both important? Because like obviously like in MNIST maybe yes, but like not in all kinds of things. The discontinuities can be important. And then also, are they assuming there's a homogeneity over the samples and over the classes in terms of the importance of this kind of lack of porosity, let's say. So we're saying like all classes should be optimizing for a similar level of non-porosity. That seems only true in this example, or that you can come up with some, but like mostly there would be different,
They can actually do either increase or decrease the porosity. So on page, I don't know, go to figure 2.
Okay.
I guess it's.
Let me find this thing. Okay, figure 2.
So in figure 2, they basically, sample points from a chain. And then B is, it decreases this loss. So it's increasing the disconnectivity, or I don't actually know how to phrase that.
But they're kind of assuming, I mean, it is still kind of, it seems like this is a parameter, and they're just assuming that a given problem, all the classes or all the problems with subproblems within it are sort of going to operate at the same level of this particular holiness, porosity, whatever you want to call it. It doesn't seem like you could actually have a kind of continuum that varies over the different classes that you're trying to label, the different parts of that figure. If you think more about a more complex natural image, there'll be parts of it that would benefit from a more continuous type of representation. Other parts would be best represented with greater kind of pixelation and porosity. I don't know. Like the pixelation can be part of the reconstruction if it's actually a crappy image.
Yes. So that actually, I think, cuts at the heart of the flaws of this paper. It's not, and I think they actually use the term loss function kind of loosely, because it really is more about a regularization parameter that controls the porosity. And that, like you said, is based on.
I think that's, so I'll say one thing. These guys have made a long history of using kind of topological vocabulary in ways that you could totally do the problem and get rid of the vocabulary. This is a regularize. And this is it's not their only kind, like going way back historically, they've been doing this forever. They're just looking for a regularizer, and they're using a kind of filtration, which is a reasonable thing to do if you're looking to regularize.
And personally, I think even all of their terminology, like filtration, okay, it's a function. Congratulations, like it's
I was going to say, it literally is not, it completely doesn't require the word filtration. It's just you're just scaling back. I mean, there's all kinds of words for this. If you were not aware of topology at all, there would be other perfectly good technical vocabulary for the zooming in and zooming out kind of.
Exactly, and I actually avoided adding the mathematical notation because it makes it even worse, because it's so abstract and somewhat meaningless. It's meaningful if you understand it, but for an audience of machine learning data scientists.
Yeah, there's just something. This is interesting because I was kind of hoping that they had gotten past that kind of slipshod approach to presenting their methods. This seems similar, It's sort of like a weird revocabularization of stuff that.
Yeah, I do have a question. Yes. So this is just a generative loss, right?
Yes. So this is just they treat the topological loss as a regularization constraint on the generated image, right? So I mean, I don't know. Yeah, I personally like the paper and I like topology. I think it does have the systemic issue of where they kind of over vocabularize. And this paper I think is especially egregious because they don't define stuff. Like they don't even talk about what a kernel is or what an image is. And like the top line of their section on homology is just, if you're unfamiliar with homology, we recommend a book. So it's, and I mean, I get it, they have to fit all that in a single paper, blah, blah, blah. And I think the idea is they want to make this as mathematically general as possible, but, you know, I actually think the same kind of arguments could be made against VAEs, where there are very specific assumptions being made in a VAE. When you do your KL divergence between your latent space and a specific distribution, say the normal distribution, 0, 1 normal distribution, you are making this huge assumption of what you want that latent space to be like. That's true in this. You are making huge assumptions about whatever you want that layer to look like, whether it's you know, porous or non-porous, has holes or doesn't have holes, whatever. I don't know. Yeah, are there other? I think that's it. Yeah. Are there other questions? It was kind of short. It's really dense.
Can it be applied to more difficult images, like scene images?
So yes, that comes down to how do you construct the complex? How do you construct the set of objects that represent your image? Now in CFAR, I would have trouble conceptualizing how to convert like all of those images, whether it's a picture of a plane or a picture of a horse, into a set of points, lines, and triangles. But there are a lot of other ways to form that complex. It doesn't just have to be points, lines, triangles. There's so many other more complicated ways to do it. It's just, I mean,
So wait, do you do that by hand yourself, or
there are libraries that do it.
automatically, right?
Yeah. It's what I described, the Simplicial complex. It's basically triangularization. You know, you break down whatever your image is, your object, into triangles, just like they do with 3D graphics and polygons. It's basically that you have these polygons and then triangles and then lines and then points.
Because I think this would be very helpful, for example, in like contrastive learning, where you want to have the same, like 2 different images of the same object. If you can like ensure that they have the same topology, it would be very helpful.
Yeah, that's a good call. Yeah, if you have 2 different versions of the same object, but you know the topological properties of that object, you know, you can break it down to some complex. That'd be interesting.
Oh, I do have a question. So in this, the application that you're looking for, like for example, you use GANs here. If you take like more complex data sets, like, let's say images, face images or something like that, they particularly take the distribution into consideration. But where I fail to understand this problem is that, I mean, I understand that it's just taking a loss function and adding a regularization, but where am I taking that topological information? Where am I connecting that topological information with the distribution or the latent space in this case? Or are we doing that at all?
Okay, so the topological information is defined by the births and deaths, right, of the persistent diagram of the object. So, we'll go back here, right? So, yeah, okay. So that's the set of topological properties. That's what you mean, right?
Yeah.
So, you know, when all of these points are born at 0 and then they die at some other radius, and that radius is the filtration. That filtration can be whatever, all sorts of different things. they have a different definition they use. I just think the Euclidean distance is the kind of simplest way to as an example. Does that answer your question?
That makes sense.
Yeah. So if you think of this birth death based on this filtration as a representation of how the topological properties persist over the filtrations, then that is kind of conceptualizing, I guess, the inner topological properties of this object. And that is what's baked into this loss function. That's why the loss function is just these lengths of the death minus the birth. I hope that makes sense. We have plenty of time left. Are there other questions? I kind of raced through it. A lot of it's, I find, both the vocabulary to be complicated and some of the ideas to be complicated, especially because as they try to make this really general, they don't talk about implementation much. And personally, I find that without having a gauge for the implementation, it can be kind of hard to conceptualize some of these things. So if there's something I glossed over that doesn't make sense.
I feel like the only topological thing which I find here is the definition between the birth and the death.
Yeah.
I mean, you need to be born in order to die.
Yeah.
So that's the only topological relation I'm finding here. Other than that, I don't know, you can maybe clear me out in this. Is there anything else that I'm missing? Like, why is this topological in that? But that's the only relation.
The relative distance between each specific points is, am I right with that?
Yeah, but the relative position also, that's the birth and the death point.
So the Euclidean distance in this diagram is just one example. I'm using it because it's the only example that I can kind of conceptualize well. But with or without this, radius, whatever your filtration mechanism is, it's about when the object, whether it's a point or a disk or a line or a triangle, is created and when it dies. And you're right, that is the only way that they represent these topological properties. Robin?
I think I'll resist commenting, but I will concur with the person. There is almost no topology here, and that is true almost categorically for this group's publications. Just as a straight example, they're using MNIST. There's only a couple of topological categories there, right? 1s, 5s, and 7s are all topologically equivalent. And they're taking advantage of the fact that people in data science actually don't have any idea what topology is, and it gets on my nerves. So I'm going to try to not over comment. I mean, I think their ideas are not bad. They just need to just come at it from a normal data science thing. We're doing this kind of radial filtration. It's a metric. It's geometry more than topology, and it's a cool idea, and it isn't topological. Particularly, except as you expand these radii, you just, you're pulling more things together and getting rid of holes or whatever.
Yeah, so I agree in that sense. I think it does capture some of the, maybe, I don't know, the atmosphere, the air of the topological properties by counting the holes in essence. But no, I agree.
Noah, they actually used MNIST, which is a classical example of a problem in which there are very few topological equivalences, and they're acting, they're mixing metaphors all over the place and assuming, I don't know, they're just assuming, I don't think I understand why they come to their problems in this way. They could absolutely have presented this paper in the context of a kind of radially varying regularizer. or something. You know, they could have presented it in the conventional language.
So
and lost almost nothing, you know.
I think the reason they didn't is because they want to be, so like the field of topological data analysis, it has a bunch of stuff to it, and a lot of it is hacky.
Like, it's really hacky. I mean, I was going to say it's not topological. I was really excited when I first came, you know, into data science and saw that they were doing this, and it was like, oh God, you know.
It's
mostly there's not a benefit. Most of these are just simply filtration driven regularizers, and I don't know. But anyway, like, I don't want to take the excitement away. I should probably log out of this one.
No, that's fine. We have 10 minutes. So I would love to hear more of your thoughts about it.
Well, I haven't read this specific paper carefully enough to kind of give the granular critique, but it's just a general, like this group, which is the group that, there's another group at Penn under, what's his name? He somehow doesn't quite take the liberties that this group does from their earliest use of the word topological in connection with data science. You know, it's just, I haven't seen anything that could not have been presented in terms that were absolutely more digestible and straightforward. And
I think they should have also put like a comparison between different losses in this case. I mean, right. I'm only seeing like the figure 10, which is like metrics for generator evaluation. In which
other regularizers, for example, right? Like other regularizations.
Yeah, I mean, that would have made it more clear for me. Right now, they're just, and again, I don't know if that's, I do not, so the topological layer that they're talking about, that's basically just, they're using a generator loss plus the regularization. I don't see, maybe I might have missed it, but I don't see a particular layer that.
If you consider the generated image as a layer, as a hidden layer, as a latent space. Because the generator generates an image, and then the loss, the topological loss is on that image, and then you have the discriminator.
The discriminator loss is what being fed to the generator in order to fool the discriminator and then create the loss. Is that?
Yeah, the gradients flow backwards from the discriminator.
Right. So maybe I'm a little bit confused by the wordings of the.
There's a whole section on the differentiation, which I thought was too much to cover, but the gradients are based off of this topological loss as well as the discriminator loss, right?
Yeah, they salvage themselves, right, by putting geometry back in, because you can't do a reconstruction that's recognizable but topologically equivalent. I mean, topological equivalences can be wildly, visually different. They can be different scales. They can be twisted around. A 2, a 9, 6, they're all the same. They're literally identical topologically. There's, from the standpoint of topology, there aren't 3 classes there.
So in this case, yes, absolutely. Like 1, 7, 3.
Right, 1, 7, 3, 4, maybe. Definitely, and arguably 2, 9, and 6 are the same. 1 and 7 and 5 are the same. So there's only a few classes from a topological perspective here at all.
And so they're not, the point is not to compare the topologies.
Yeah, I know that. Yeah,
right? It's to retain the properties, because as you see in the generator, like it loses a lot of its shape. You know, let's say the top left, that 1, I think it is it's, I think you would agree, like it's now topologically not a 1.
Wait, which one? In C?
In A, in the top left, that's the baseline generator.
Oh, I see. Okay. I don't know. It's just it's just pixelated more than, I mean, it's hard to even know what it is topologically at that, right? Like it's junky.
Yeah, I mean, it's definitely hacky.
I'm not sure. But the other thing, I guess, like now that I'm thinking a little more, what they're doing is they're not talking about topology in an object-wise sense, right? They're really talking about it in a point-wise sense.
Yes.
And there's nothing about the final topology of the quote object or the class that they care about. Otherwise, there would only be 3 classes to classify here. But what they're talking about is just at a hyper local level.
Yes.
Nearest neighbor relations. I mean, it exists, you know, you could call it something so different. It's nearest neighbor at different radii. That you do this with UMAP does this. TSNE does this. This is a thing.
They made it general so you can use any filtration and any complex. Their examples use simplicials and the radial.
Yeah, I understand, you know, but like somehow, like you said, the implementation would be kind of complicated or
so they could have taken the perspective of like, we're just going to use the radial filtration and you know, break this thing down into local points. But because they want to be fancy, and I don't know, maybe their take is erroneous, maybe they're maybe they're wrong, I don't know.
You know, yeah, it doesn't feel, I don't think what they're saying is incorrect. It's just being cast in such a bizarre and deceptive way, as it could have been simply presented as a radially expanding, like a kind of graded radial regularizer. And they could have just, if none of them had ever heard a topological word in their life, they still could have written this paper perfectly well. They just pull out the homology because it's totally not needed. You know, it really is a different way of talking about kind of graded resolution filtrations. You know, like you don't really need, it's not really necessary. You know, they could have written it without.
So the guy, Gabrielson, is a topologist.
And Gunnarsson is a famous topologist from before he went rogue in this way.
Yeah. And so they are like actual topologists, and
that's what makes it egregious. I'm so like, that literally is what's wrong.
Well, let me ask you this. So if you remove the cases, if you remove like, oh, they're not even going to talk about the specific filtration. They're just going to talk about it in the general sense. The paper is a lot less useful and is now practically useless, but it's more abstractly correct.
Yeah. They might have like, and you know, and also I do know more, like this is so consistent with things I've seen from them from early on, and it's very disappointing because they're topologists. At least Carlson is, and almost often his co-authors are. And it's fine, you know, like, I mean, you could present this, like, at the end of the day, it doesn't particularly matter if someone wants to use it, whether they use topological vocabulary or more functional analytic vocabulary, things like, you know, continuity and, you know, granularity, and there's all kinds of other ways you could talk about this, but like, and you can use it either way. It just feels so salesy, you know, like, I'm just gonna throw this, why? You can do it without, like, all of this is fine.
And I don't know how helpful topological data analysis is. And I mean, like, I just don't know. I don't know enough about the research.
I've seen some work with, you know, kind of filtrations, especially on graphs, which is the most trivial topology. It's not even considered topology by topologists. It's considered that trivial. It's the degenerate case of topology. But at the same time, when they stay in the degenerate world of graphs and you do filtrations and there are well-defined, the graph itself is telling you where the neighbors are rather than using the geometry. You can, I don't know, you can learn things that are kind of things you could learn other ways too, but it's not useless. I don't know. I just think we could do something kind of fun with topology in data science, and they're not, you know.
So I'm sure there are ways to break down images into better complexes, right? Like instead of just points and lines.
Right, but then they collapse. Then you have like almost everything is the same topological object, right? But I mean, you can't have it both ways. You can't be playing in a topological sandbox and then set it up so that you've collapsed, most of your classes into a couple of categories when you actually wanted them not to be. Like, it doesn't serve the purpose any longer and it wouldn't recognize a topological equivalence. You could, for example, even if 9s, 6s, and 2s were considered one class for their purposes, what about the something that's not even a digit, right? Like, there's a gazillion things that are topologically equivalent to a 9. Most of them don't look anything like a 9, a 6, or a 2. Would it properly generate the class? Because the class includes things that look nothing like a digit at all. And, I don't know. But anyway, I'll step now. I have my own issues with these guys, so I'll let everyone else kind of have their say.
Sure. Yeah, I mean, I don't know. I think basically the whole paper was like, we're going to talk about this in general terms. Topological data analysis has a fair amount of hacks. We're going to implement it with some of those hacks and then let the reader decide. And I don't know, are there other questions? Okay, exactly one. Okay, thanks guys.